Hey, what's up, guys? I thought I'd go over some of these multiple choice with you. To be honest, there aren't multiple choice problems that are this hard on the test, but it's good stuff to be able to do. All right, I told Block 1 I made it hard on purpose. I knew I picked hard problems. We won't talk about this morning so much of what happened when we were reviewing the problems, other than to say Sierra Spring is a champion for bailing me out at one point. So anyway, question 1. I'm just going to go through them, all right? So you do your best if you want to skip along. Look for the number of the question you want to review in the corner. All right, two satellites circular orbit around Earth. The distance from A's center is twice that of B, the ratio of speeds. Well, speeds and orbital stuff. I know we're going to go with this. Start that, and then let's see. This is G, mass of the satellite, mass of the planet, R squared is mass of the satellite, V squared over R. Sorry, I should have this as just plain old R. So V is that. Okay? The big deal, I mean, what you have to be able to get used to is this idea here, that B and R are related with the square root. Okay? So if the radius of B, hang on, distance to A center, the radius of A is twice the radius of B. Well, since R is underneath here, it's underneath the square root. There's a square root thing going on. Okay? So that means that in your answer, there's got to be a square root. And since, we have the 2 that's going to be in this square root, there's a square root of 2 factor. All right? Now, you can go through some algebra to do this, but what I'm trying to get you to realize, when we're doing these problems, especially in May, you don't have much time, the idea is to recognize, okay, there's a 2, but it's under this square root. So that's got to be one of my answers. It's got to be either D or E. All right, now what we know the other day is we watched things orbit. We looked at some animations of some orbits, right? And the closer you are in here, the faster V is. Out here, we'll say that V is something like that. All right, so since A is farther away than B, A's got to go slower. So the ratio of the speed has to be that, VA to VB, right? This has to be, A has to be slower than B. Okay? And again, it's a square root thing because R is under that radical sign. Fair enough? Okay, next. 2. This shouldn't take long. 2 satellites, blah, 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 distance, oh yeah, okay. So we said, again, we can go to here that the velocity is how about this? Velocity squared is G, mass of the planet, over R. All right? So we'll call this like 1 and 1, and then V2 squared, G, mass of the planet, over R2. Well, here's what we figured out in block 1. This is the same no matter what. So that means that V1 squared R1 is V2 squared R2. So therefore, we're looking for the distance from satellite B, so that's R2, is R1 times V1 squared over V2 squared. There's your answer. That would be D, correct? D. Nice, now we're rolling. Number 3. Object tied to a spring moves in a circular path at a constant speed, which the following statement says accurate. Net force is 0? No, not accurate. Acceleration is 0? No, not accurate. Ooh, acceleration is constant? Also not accurate. All right, the acceleration of the object anywhere on this circle, acceleration is like this, acceleration is like that, acceleration accelerations like that. The direction constantly changes, even of the acceleration. So this has a non-constant acceleration. So none of those are true. None of those are true. 4. Centripetal acceleration of a ball swinging around a string when it passes 1 revolution in 5 seconds, and the radius is 1 meter. 1 revolution in 5 seconds. Well, that's a period, right? Amount of time for one thing to happen. And radius 1 meter. We want the centripetal acceleration. V squared over r. Or, since V is 2 pi r over t, hopefully you're okay with the fact that that comes out to 4 pi squared r over t squared. We should have seen that before. So let's see, 4 pi squared times r over t squared. So there it is. Well, it's 4 pi over 25 meters per second squared. So which one is that? That looks like E. The lines there mean divided by. They try to do it under. Yeah, it's E. Well, more importantly, that's the answer. 5. Ball attached to a string, whirled around a circle, radius r, velocity v. The radius is changed to 2r. Oh, and the force is doubled. So this is, let's see, F is mv squared over r. We're talking about changing those things. Let's see, we double so r to 2r, that would make f go to f over 2, right? Or that would divide us by 2. Changing, f, well, let me forget this. I forgot we're changing f, I'm looking for v. So f goes to 2f, right? The centripetal force is doubled. We want to know what happens to v. Well, what I would do is write this in terms of v then, or solve this for v. F r over m. Well, if we double r and double f, that means we're increasing this by a factor of 4. But it's under the square root. So the new speed, 2v. Okay? Okay. 6. Engineer wishes to design a roller coaster which will have no effect on whether the car remains on the track. Well, let's see. All right. If you do something like this at the top here, well, let's see. We got mg, we got n, and hang on. Yeah. Well, we're going to get, let's see, mg minus n is mv squared over r. Notice, we can actually get rid of this and have the cars stay on there just because of gravitational force. Oh boy. So, what doesn't matter? The mass. Right? Fat people, skinny people, they all do the same thing. It's not like the skinny people go flying off and the fat people don't. Right? Excuse me. The larger people and the lighter people. Okay? So that's C, the mass. 7. Ball of mass M, rotating on a string, radius R, period T. What's the tension? Well, tension in this case is going to be FC, is going to be MAC, is going to be MV squared over R, is going to be, well, this is, again, here's A, so keep that mass. Remember our acceleration? 4 pi squared R over T squared? I think that's the answer. Yeah, 4m pi squared R over T squared E. No, not E, D. Forgot the square of the pi. Okay? Oh, yeah. 8. I love it. 8. Direction of the frictional force. To the left, inward. 9. If A centripetal force Fc, notice how A is italicized? That's weird. If a centripetal force Fc is acting on the satellite, then its speed is equal to, well, we could write this. Fc is mv squared over r, where this is the mass of the satellite. Yes, normally we'd write this as Fg, gmm over r squared, but in this case they tell us a centripetal force Fc. Well, just solve for speed. Fc r over m equals v. This is number 9, I'm sorry. And that's A. That's A. Okay? Okay. 10. Which of the following is true? Of the velocity and acceleration vectors for something moving in a blah, blah, blah. They are always perpendicular. C. Always true, right? B is always tangent. Oh, yeah. Not that great. So, yeah, V is always tangent. A is always centripetal. Always perpendicular no matter what. That is C. Onward. This doesn't take so long. 11. This thing rolls down a path and the path stops. The object is then horizontally launched because it has a tangential velocity, so then it turns into a horizontally launched projectile. That's C for number 11. 12. Oh, now this one. Do I need this thing here? Speed. Yeah, let's see. This one you actually need conservation of energy. So you can solve it, which I encourage you to, but you don't need to do it for tomorrow. Skip. 13. Distance between the center of gravity and satellite is halved, and the mass is doubled. Then the force. Okay, so we're looking at F. Mass of the planet, mass of the satellite, separation squared. Let's see here. Distance is halved. So changing r, that's going to give us F times 4. If this gets 2 times smaller, F gets 2 squared times bigger. And the mass of the satellite is doubled. That's going to give us twice the, what do you call it? That means that increased by a factor of 8. All right? Booyah. 14. Ooh, a spaceship fires a weapon at a planet, destroying half its mass. The planet's inhabitants would find that half of them were dead. Excuse me. They're looking for their weight, right, or their mass. Well, the inhabitants' masses wouldn't change. Their weights would, because their weights, really gravitational force, is mg. Well, the question is, what happens to g if half the planet's mass goes away? Well, we should be okay with this. Whoops. So if mass decreases by a factor of 2, then g decreases by a factor of 2. That means the weight decreases by a factor of 2. Right? So that means the mass has been decreased by, weight by a factor of 2. See? Okay? 16. Gravitational force F exists between points A and B. Point objects in distance r. Mass of the A is doubled, and distance r is tripled. What's the new gravitational force? Well, let's see. We're back to one of these. 15 F G M over r squared. So let's see. Double the mass, that's going to give us times 2. Triple the separation, that's going to give us divided by 9. So the new one is, well, 2/9 F. Yeah? A. Good? Good. 16. Mass M above the versus drop from. This is the one we did that conservation of energy one for this. Alright? Whoops, not net energy. Total, I guess. We did ME initial is ME final. Really not what I expect from you tomorrow. Alright, but it does work out, I believe, to A. But don't worry about that. A moon with mass M. This is all gravitational stuff. Sort of. No, I guess. A moon with mass M above the surface of Earth, mass M, is dropped to... Oh, well, we just did that one, right? That's the same problem as... I don't know, I'm literally reading the same problem. A moon with mass M is orbiting a planet of mass 10m. The ratio of the force the planet exerts on the moon to the force the moon exerts on the planet. Of course, right? So here's the planet, 10m. Here's the moon, m. Of course, these are two objects that exert forces on each other. The forces are equal and opposite. Don't miss that one. Equal and opposite. Okay? Okay? 18. Which of the following statements explains why astronauts feel weightless while orbiting the Earth? Well, it's because the spaceship's in freefall. Alright? If you are standing in an elevator and the elevator cable breaks, snap! Universal sign for string breaks. Well, the elevator will accelerate downward at 9.8 meters per second. You will accelerate downward at 9.8 meters per second. And the floor, therefore, will not push up on you. You are not weightless, but you will feel like it because there's no normal force exerted by the floor. Okay? A person weighing 600 newtons on Earth travels to a planet with 4 times the mass and twice the radius. The person's weight, well, I know they're asking for this. Weight is a gravitational force, is mg. So what happens to g? Well, we can really just do this, right? This is g m over r squared. So here's u, here's the planet. Right? So if we, in the second one, we have 4 times the mass, so mass u, 4 mass of the planet, and the person's, and twice the radius. Careful, watch this. The whole thing squared. Well, that's g, mass of u, 4 mass of the planet over 4r squared. Same. C, 600 newtons. 20. The moon orbits a planet in a circular orbit of radius r. The mass of the planet m. What's the period? Ooh, the period of the moon's revolution. Yikes. Let's see. Oh, I know this one. This is Kepler's third law. I bet we can do this. Fg is MAC. G, mass of the satellite, mass of the planet, r squared, mass of the satellite, v squared over r, mass of the satellite, r, v squared is g, mass of the planet over r. Well, we want something about period. Period lives in here. This is 2 pi r over t squared. Right? 4 pi squared r squared over t squared is g mass of the planet divided by r. We want t, so let's see, that's going to be, check it out, 4 pi squared r cubed is t squared g mass of the planet. It's actually Kepler's third law. Kepler's third law says, and it's a mouthful, the square of the average orbital period of any planetary orbit is directly related to the cube of its semi-major axis. Yeah, Kepler's third law. So if we want an expression for t, it's going to be 4 pi squared r cubed over g mass of the planet square root. That looks like, oh, good. We can, I believe we can, that means, yeah, we can take this out of there, right? 2 pi times r cubed over g mp. Yeah, that's the, yeah, d. Good. Good? Good. 21. Satellite orbiting around the Earth at a radius 2r from the center. What's the magnitude of the velocity it's traveling at? Well, let's see. That's going to be fg. Get sick of this yet? Is mac g mass of the planet over r is v squared. I'm skipping steps. But it's really 2r. Yeah, that's it. Right? Okay. Man, that was a lot faster than I thought. How fast? 22 minutes. About a minute a question. Hey, man, that's about the pace you want to. That's about the pace you need to do questions after in the AP exam. Wow. That's no joke. But there's some doozies in here for sure. Okay. We'll pick a few. We'll pick a few for the exam, for the test. All right. But not many. I'll see you on Tuesday, folks. Later.